Hi folks, so two more questions here. We'll look at the 2019 question on acids and bases and then the 2017 question on acids and bases, predominantly the calculation. So the first thing here, use equations to show that when dissolved in water, HCl acts as a Bronsted-Lowry acid. Now once we see a Bronsted-Lowry acid, we're thinking there it's a proton donor. So I've got my HCl, dissolving it in water. It's a proton donor is hydrochloric acid, so it's giving away a H+. And what we're left with then is Cl- and H3O+ is my products, my hydronium ion. Next one, NH3 or ammonia acts as a Bronsted-Lowry base. So NH3, it's a weak base. And with water, doesn't matter what arrow, we don't need to be fussy there. And since it's a base, it's a proton acceptor. So it accepts a H+. Remember, just simply because it's a reversible reaction, we're using that there. And what we're left with is NH4+, our ammonium ion, and OH-. Part 3, explain why HCl is a weak conjugate base. So there's something you might have learned there, the theory. The stronger the acid, the weaker the conjugate base. So I'll just write that simply. It's a strong acid. So you just elaborate there and say the stronger the acid, the weaker the conjugate base. And that leads us into the IV there. Ammonia has a strong conjugate acid. And the reasons I got that, think of your opposites there. It is a weak base. So the weaker the base, the stronger the conjugate acid. So again, elaborate that up for yourselves. Part B, pure water self-ionizes as follows. Here we're given a table of values with our Kw. And we can see there as we increase the temperature, we increase the value of Kw. Just look at the numbers, 0.1, 0.3, 0.7, 1.4. So the values there increases as the temperature increases. So the degree water breaks down, if we increase the temperature, we're pushing that reaction to the right, going into the products. So the equilibrium shifts right when the temperature increases. And that means that this forward reaction is endothermic. And that comes up later on anyway. So write the self-ionization constant expression for water. So the first bit there, part 1, Kw is equal to H+ times OH-. And you need your square brackets. Sometimes they ask you to define that. It's the product. Product means multiply. It's the product of the molar concentrations. Them square brackets mean moles per litre. So it's the product of the molar concentrations of hydrogen ions and hydroxide ions. The data in the table consisted with the self-ionization water being exothermic or an endothermic. As we said there, it's an endothermic. Always have a punt. You have a 50-50 chance. You just won't get the justifying bit. It's endothermic. As you increase the temperature, you just write this properly. As you increase the temperature, values increase. Equilibrium shifts to the right. And the dissociation increases. So the breakdown of water into your hydrogen ions and your hydroxide ions increases. So overall, it's an endothermic reaction. I love this thing. Equilibrium shifts to the right hand side. Plot a graph. I'm not going to do that with you. It's handy. Just put maybe your temperature. When you see a graph, you're rubbing your hands. Maybe put your temperature on your x-axis in degrees Celsius and your Kw in the y and whatever. I was looking up the American scheme to shoot. So you could have copy and paste the picture in there, but I couldn't. There was none up. So plot a graph. Again, just look at your figures, the Kw, the 0.1, 0.3. They're the ones that matter. So maybe go up in ones or halves if your graph paper enables you. And in your units, you could say that is by 10 to the minus 14, you know. Use your graph to predict the value of Kw. Now, I looked up the American scheme there. For IV, they give you anything between 2.1 by 10 to the minus 14 all the way to 2.5 by 10 to the minus 14. Now, all you'll have to do there is at 37 degrees, go up from 37 to where it hits the graph and go across. Read it off and hope that it spits out an answer anywhere between 2.1 and 2.5. So for the remaining bits of these calculations, I'm going to use the value of 2.3 by 10 to the minus 14. Lobbed halfway between those two. So for V, now I'm actually going to do some work. Use this value. So my value of Kw there is 2.3 by 10 to the minus 14. Use this value to calculate the H3O plus, which is the same as H plus, concentration of pure water. Now once I see it's pure water, that means if you ever see pure, that implies that your hydrogen ion, or your H3O plus, and your hydroxide ions are in the same amount. Now we mentioned there in part 1 that Kw is equal to the product of the molar concentrations of hydrogen ions times hydroxide ions. Now we know at that temperature that Kw is 2.3 by 10 to the minus 14. Since it's pure water, these two fellas, the H plus and the OH minus, are in the same amounts. So a lot of the time you might see, or if you're thinking of maths, what might we call that if we're working it out? X. And they're both X because they're both the same. So they are equal to X times X, and X times X is X squared. So to work out what X is, it's the square root of that root of a number. And we throw that into our calculator. 1.52 by 10 to the minus 7. That's equal to our H3O plus, since specifically that's what it asked, which is also the same as our OH minus. They're both the same because it's pure water. Next one, VI. The pH of pure water is close to 6.77 at one of the temperatures in the table. Find by calculation this temperature. Now in order to get the temperature, we need to get the Kw. So the first thing what they've given me, they've told me there, work with what they've given you, pH is 6.77. How do we say the pH? What's our formula for pH in chemistry? It's the negative log to the base 10 of the hydrogen ion concentration. Now we're going to work out our hydrogen ion concentration. First thing we do, remember, just bring that minus across to the other side. So log to the base 10 of our hydrogen ion concentration is equal to minus 6.77. You can use your anti-log or use what I use. Liverpool beats Newcastle powerful. Remember your B just stands for your base. There's my power. And my number there is H plus. So I'll throw that to my calculator, or the anti-log, shift log, minus 6.77. 1.7, say, by 10 to the minus 7. 1.7 by 10 to the minus 7 is equal to H plus. Now, since it's pure water, once again, pure water. What does the pure mean? If you see pure, it's all these key words. Your hydrogen ions and your hydroxide ions are equal. So we need to get our Kw because they've asked me for temperature there. So Kw is the product of the molar concentrations of those two. So Kw is equal to 1.7 by 10 to the minus 7 squared, or 1.7 by 10 to the minus 7. So we throw that in our calculator. So I'm just going to say answer squared. I get 2.88 by 10 to the minus 14. Is my Kw value. And then you could use your graph there, go across from my Kw and go down. Since I don't have the graph, I'm looking here. It's going to be around 40 degrees. Because 2.88 is the same as 2.9 by 10 to the minus 14 to one decimal place. So therefore, 40 degrees Celsius. So a few wee hairy calculations there. One more set, we'll look at 2017 for ourselves now. So 2017. Again, a wee bit of theory at the start. Define a base according to Bronsted-Lowry theory. So a Bronsted-Lowry theory is, our Bronsted-Lowry base is a proton acceptor. So learn them perfectly. A conjugate acid-base pair is an acid and a base that differ by a proton. or an acid and base that differ by the presence or absence of a proton. This one, what is the conjugate acid? A for acid, A for added. So we add on a H plus and we get H3O plus, or hydronium ion. B, define pH. May as well get the calculation bit in, or the definition is, it's the negative log to the base 10 of your hydrogen ion concentration. So get your words from that formula. So it's the negative log to the base 10 of the hydrogen ion concentration. If you like, you could say it's the negative log to the base 10 of the hydrogen ion concentration in moles per litre. If you're thinking that wasn't hard enough. Now we're into a tough wee one here. I'm not going to do C because it's drawing a graph again, and I'm not that good at computers. I've only moved on from a foam roller. So the pH values of 0.1 molar solutions of sulfuric acid, hydrochloric acid, and methanoic acid are that, and that respectively. So there's my sulfuric acid, respectively, just means in order. There's my hydrochloric acid. There's my methanoic acid. In terms of hydrogen ions, account for the difference in pH values. Now the thing here is, it's looking at in sulfuric acid, it's got a dibasic acid. In hydrochloric acid, it's got a monobasic acid. And a methanoic acid, it's got a weak acid found in nettle or ant stings. So in part 1, in terms of hydrogen ions, account for the difference in 0.1 molar HCl and 0.1 molar sulfuric acid. So if I had hydrochloric acid, it's a strong acid, it fully dissociates. And it dissociates into H plus and Cl minus. So it's in a 1:1:1 ratio. Now here, I have 0.1 molar, so 0.1 molar HCl gives me 0.1 molar hydrogen ions. I'm supposed to say dissociates. Dissociates into 0.1 molar hydrogen ions. It's fully dissociates, as it's a strong acid. Now if I look at sulfuric acid, it's a dibasic acid. So anytime you see sulfuric acid in your acids or bases, this is what's kind of going to throw people off. So it splits up into 2H plus and your sulfate anion. So I always think that's a 1:2 ratio. So if I have 0.1 molar sulfuric acid, I'm going to produce 0.2 molar hydrogen ions. Now you could use your antilog there and you'll get a value of around 0.2 as well. When you do your antilog of 0.7, you'll get a similar answer here. So 0.1 molar sulfuric acid dissociates into 0.2 molar hydrogen ions. Now the next bit of this is comparing your hydrochloric acid, which we've done, with methanoic acid. Now methanoic acid is a weak acid. You know it's a weak acid because even if you look ahead, it's given a Ka value. Anything with a Ka value is a weak acid because it doesn't fully dissociate. So they've provided me there that the pH of methanoic acid is 2.37. Now what we wrote down when we defined pH, it's the negative log to the base 10 of our hydrogen ions. It's the same few formulas that you use. I'm going to work out the concentration of hydrogen ions that's produced from that 0.1 molar methanoic acid. So bring across that minus first of all. And then do your anti-log. Or I'm a creature of habit. I do my Liverpool beats Newcastle. So my base is 10 to the power of minus 2.37 is equal to my hydrogen ions. I throw that in my calculator. So shift log minus 2.37 and I get 4.27 by 10 to the minus 3. It's my concentration of hydrogen ions. So when I'm discussing that, my weak acid, methanoic acid, 0.1 molar methanoic acid, you could say there partially dissociates to give 4.27 by 10 to the minus 3 hydrogen ions. You know, it only slightly dissociates, so weakly dissociates. So that's them first two bits done. Difficult enough. I would probably, if that was me in the exam, I'd write about my HCl once again down here. You know, take nothing for granted. 12 marks. You're assuming maybe 6 up here, 6 up here. So I'd write in about my HCl once again. Part 3. Use the pH values for 0.1 molar methanoic acid to calculate the value of Ka. Now, there's a thing for weak acids. Weak acids, to work out my hydrogen ions, it's a square root of gamma, Ka times Ma. Now that's what I'm trying to work out. Now I know my hydrogen ion concentration, I worked it out in the previous bit, is 4.27 by 10 to the minus 3. Now this is a tough question. This is square root of Ka, the molarity there is 0.1. Now how do I get rid of that square root? How you get rid of the square root is you square both sides. And that leaves me with 4.27 10 to the minus 3 squared is equal to 0.1 Ka. Now to work out Ka, I'm just going to divide. You know, if I had 2x equal to 8, I would work out x, it's 8 over 2. It's the same thing here, except my x is replaced by Ka, and my 0.1 is my 2. So I divide by the number stuck onto it, 4.27 by 10 to the minus 3 squared over 0.1 is equal to Ka. Never delete them numbers in your calculator. Look at that. So I'm going to press my fraction, my answer squared over 0.1, and I get 1.82 by 10 to the minus 4 as my value of Ka, which doesn't look absurd, so I'm happy with it. And then the last bit of that question, the pH of 0.05 molar methanoic acid. I just wrote down for myself, anytime they ask me the pH or give me something with pH, again, creature of habits, write down what pH means. The negative log to the base 10 of hydrogen ion concentrations. By doing that, I know I'm going to have to work out my hydrogen ions. And for a weak base, my hydrogen ions, square root of Ka times Ma. I'm going to use my answer of the Ka from that I worked out in part 3. So it's square root of 1.82 by 10 to the minus 4 times my Ma, which is 0.05, which they told me in the question. So real tough. For 3 sort of questions, if you struggle with the sums, I'd maybe steer clear of these here. Again, I haven't deleted it by good luck. I'm going to multiply that answer by 0.05, take the square root of it, and I get 3.02 by 10 to the minus 3. It's my concentration of my hydrogen ions, and then your pH is your minus log to your base 10 of your hydrogen ions. So minus log to the base 10 of 3.02 by 10 to the minus 3. Throw that in your calculator, press minus. You're going to have to delete both of those. Minus log answer 2.52. Smashing. Looks sensational. 2.52 is my pH. And that's it. Real tough questions there. They're foot 3. But as I say, some people would love them. You know, you're just manipulating between the formulas. pH is the negative log to the base 10 of your hydrogen ion concentration. There you're looking at your monobasic, your dibasic acids, so your strong acids fully dissociating, and working up into your 2H plus, so your 3H plus if it was phosphoric acid, H3PO4. Once you see your Ka, you know it's a weak base, so your square root of gamma comes into play there. So tough. I'd be maybe looking at doing these questions after I go through maybe previous years, easier years. This is the tough ones like here.